So hello everybody and welcome back to a brand new video, and in this video I will be covering problem D, that was 2 plus dose from round 816. Yeah, so let's get started with the problem. So in the problem we have been given the size of an array n, right? So our array is a1, a2, a3, so on up to n. We currently don't know the array. We have to find the array, right? And to find the array, we have been given some Q equations or Q statements, right? Where each statement has three variables, I, J, and X, right? So if you have been given a statement Q, you will be given three variables in each statement, I, J, and X, which means that A of I bitwise or A of j is equal to x, right? So you have been given Q statements of the following type, and you have to use these Q statements to find your array A, and you have to find the lexicographically minimal array A. To find the lexicographically minimal array A. So that is the problem. So given the size of the array and Q statements of form AI or AJ is equal to x, we have to find the lexicographically minimal array A that will satisfy all the Q statements, right? So that is the problem. So how can we solve this? So before we start with the solution, let's see some observations, right? The very first observation is that the bits are independent, right? Bits are independent of each other. What that means is when you do a bitwise OR, for example, if you have 1 0 0 1 and you have 1 1 0 0, right? If you do a bitwise OR of these, right, you do a bitwise OR, you will get 1 0 1 1. So if you see, we are finding bit 0 differently, we are finding bit 1 differently, bit 2 differently, and bit 3 different, right? So these bits are not interfering with each other, right? So bits are independent of each other. So that is the first thing, right? So when we are trying to find the array A, we don't need to find all the bits together, right? First we can find bit 0, first we can find bit 0, then we can find bit 1, then we can find bit 2, and so on up to bit 30, right? So you don't need to think about all the bits at once. So you will take first one bit, you will figure out that bit for all the numbers, right? And then we can figure out all the bits in the same manner, right? So our approach will be, first find minimal bit 0 configuration or values for array A, and then repeat the same process, for all the bits. So that will be our approach. So first of all, we need to find this minimal configuration for bit 0, right? So going forward, I will just talk about bit 0, right? And you can apply the same method for all the bits, right? So first of all, we have to find the minimal bit 0, the bit configuration for the 0th bit, right? So how can we do that? So instead of seeing these as statements, right? So you have been given a statement of type I, J, and X, right? So that is A of I or A of J is equal to X, right? So if you try to see these as statements, it won't help, right? Because there can be some interconnections and that will be hard to track, right? So instead of seeing this statement, you can see this as a graph. So if you see this as a graph, it will help you in keeping track of edges, right? And bitwise all that stuff like that, right? So instead of seeing these as statements, you can see them as graph nodes or edges. So we will try to convert these statements into a graph and then try to solve this graph. So we will convert the statements into a graph, and it is easier to solve a graph, right? It is easier to solve a graph instead of some statements, right? So we will make the statements into a graph and then we will try to solve that graph, right? So Let's take some example from the problem itself. So we have the following example: 4, 3. We have 4 nodes with 3 statements, right? So this is my n, this is my q, and then the 3 statements are 1, 2, 3, 1, 3, 2, 1, 2, 3, 1, 3, 2, and 4, 1, 2, 4, 1, 2, right? So this is in binary, this is 1, 1, this is 1, 0, and this is 1, 0, right? So we are currently only solving for the 0th bit, right? So we don't care about the first bits for now. So we have the statement 1, 2, 3. So that means there is an edge between node 1 and node 2 such that the bitwise OR of these values is how much? It is 1, right? Similarly, we have a node between node 1 and node 3. We have an edge between node 1 and node 3 where bitwise OR is how much? Bitwise OR is 0. Again, I am saying that we are only thinking about bit 0 now, right? You can apply the same process for all the bits, right? So currently we are only solving for bit 0. Similarly, we have a node between 4 and 1. We have a node between 4 and 1, right? Again, the bitwise OR is 0, right? So first of all, if you think about the edges that have a weight 0, that means that the bitwise OR of the two values is 0, right? If your edge weight is 0, is equal to 0, that means AI or AJ for that bit, let's say bit 0, is equal to 0. That means both AI and AJ have bit 0 equal to 0, right? Because that is the only way you can have OR equal to 0, right? So first of all, we will form a graph. So we have a graph here. This is 1, this is 0, right? We know that if a edge has a weight of 0, then their bitwise OR is 0. That means both the bits are 0 in both the numbers, right? So that is the very first observation, right? So the very first observation is that if edge weight is equal to 0, then the bit is equal to 0 in both the nodes, right? For example, if you have a 0 here and we have a 0 here, then that means our bit 0 is equal to 0 in node 1 and our bit 0 is equal to 0 in node 4 as well. Similarly, bit 0 is 0 in node number 3 as well, right? So now we have made 3 nodes equal to 0, right? Currently we don't know the value of bit 2, right? The value of bit 0 for node 2. So we will assume it is 1 for now, right? So we have done the first step. So in first step, you will go over all the edge weight that are equal to 0 and then set bit equal to 0 for both the nodes that are connected via that edge, right? So that is the first step. Then we'll go to step 2, right? As you have to find the minimal bit configuration, you can again iterate over the nodes and set a redundant 1s to 0s, right? What I mean by that is, so to show you the second step, I will have to take an example. So let me take an example. Let's say you have a graph something like this. We have a 1 here, right? Let's say we have a 1 here. We have a second node here, right? We have a third node here, and this is again 1, right? So first of all, we will perform step 1. So wherever edge weight is equal to 0, we will set bits equal to 0 in both nodes connected via that edge. But as you can see, there are no edges that are connected with a weight 0, right? So our step 1 will not be used here, right? So let's move on to step 2. So our step 2 was, we had to iterate over the nodes again and set the redundant 1s to 0s. So currently we are assuming that all of these are ones. All of these are ones. So bit 0 is also 1 here. Bit 0 is also 1 here. Right. So now we have to set redundant ones to zeros. Right. So we have to find the lexicographically minimal array. So we will start with node 1. Right. And we will iterate over all the edges. Right. So if you see here, my bit 0 is equal to 1 here. My bit 0 is equal to 1 here, and I also have a 1 here, right? So my 2 is already contributing to the following one, right? So my 2 is already contributing to the following one. Similarly, if you check for 3, my bit 0 in 3 is 1, and it is already contributing to the following edge. It is already contributing to the following edge. So as you can see, the following one is not contributing to anything, right? The following one is not contributing to anything. So if I can set this to 0. If I set this to 0, it won't change anything, right? It won't change anything because the following one was not contributing to any edge, right? So now I can set this bit to 0. So I have my node 1 here, my node 2, node 3 here. So bit 0 is equal to 1 here, bit 0 is equal to 1 here. And now I have set this my bit 0 equal to 0 here, right? Because the following bit was not contributing to any edge. So now we are done for node 0, right? So now we can move on to node 2. So if you check for node 2, right, I will iterate over the following edge. If you see here, the 0 is not contributing to the 1, right? The 0 is not contributing to the 1. So the 1 itself is contributing. The 1 itself is contributing to the one on the edge, right? So the following one is not redundant, because it is contributing to an edge. It is contributing to an edge. Similarly, the one here is contributing the following edge, right? So the following one is not redundant as well, right? So our final answer will be how much? Our bit 0 will be 0 in 1, and our bit 0 will be set in node 2 and node 3, right? So that is how we will solve this. So let's move on to our the first example that we were solving and try to do the same steps on that graph, right? So let's try to solve the same graph using that. So our first graph was, we had a 1 here, we had a 2 here, we are currently solving for bit 0, right? We had a 3 here, we had a 4 here. So we have a 0 here, a 0 here, a 1 here. So first of all, we will apply step 1, right? So if you apply step 1, we will have a, first of all, they were all ones, right? First of all, they were all ones, right? On the nodes, right? So we will apply step 1, and for all the edge weights that have 0, we will set the nodes to 0 as well. So I will set this to 0, right? Because of the following edge. So I will set this to 0, and I will set this to 0 as well, right? So that was step 1. So now we move on to step 2, right? And now we have to check for the useless ones, right? So I already have a 0 here, so I don't need to think about this. I already have a 0 here. I already have a 0 here. So now I need to think about the following one. Is the following one useful or not? So if you see, the following one is contributing to the following edge, right? So the one is contributing to an edge, right? So this is not redundant. This is useful. The following one is not redundant, right? So it will stay, right? So now for the array, we have found the value of bit zeros, right? So my first node has 0. My second node has 1, my third and fourth node has 0 and 0 as well, right? So now I need to do the same step for bit the second bit. So now let's do the same step for the second bit. We have a graph here. Right? So now let's move on to our weights here. We have a 1, we have a 1, we have a 1, right? So all the edges have a weight of 1 here. All the edges have a weight of 1. 1, 1, 1. And currently I'm assuming all the bits are 1 as well. So now we are iterating for bit 1, right? So if you try to apply step 1 here, right, there are no edges with weight 0. So we can just skip step 1. So now let's move on to step 2, and now let's try to remove the useless ones, right? So if you see this 1 here, right, is this 1 useful or not? So if you see, the 2 is already contributing to the 1, right? The 1 is already contributing to the edge, right? The following one is contributing to the following edge. The following one is contributing to the following edge, right? So the following one is not contributing to any any of the edges, right? So the following one is useless. The following one is useless. So we can just set this to 0. We can set this to 0, right? So if you go to 2 now, right? If you go to 2 now, it is the following one is contributing to the following edge. So it is useful. This one is useful. Similarly, the following one is contributing to the following edge. So it is useful. And if you go to here 4, the following one is contributing to the following edge. So it is also useful, right? So now we also know value of bit 0, right? Sorry, we also know value of bit 1 now, right? So for node 1 it is 0, for node 1 it is 0, for node 2 it is 1, for node 3 it is also 1, and for node 4 it is also 1, right? So now we know our array. Our array is how much? First value is 0, the second value is 3, the third value is 2, and the fourth value is also 2, right? So now I have my following array 0, 3, 2, 2. And if you see the answer here again, it is again 0, 3, 2, 2, right? So we were able to find, first we found the answer for bit 0, then we found the answer for bit 1, and then we combined those answers and we got our final answer, right? So that is the solution to the problem, and I will summarize it once again. So the summary is, bits are independent, right? Because OR operation is independent, right? So we can solve for each bit independently. We can solve for each bit separately. So for each bit, we will create a graph. For each bit, create a graph from statements. So if you have a statement like I, j, and x, then there will be a node between I and j. And if let's say we are solving for, let's say, some bit b, right? Then here it will be a value of bit b for x, bit b value for x, right? And here in the starting we will assume that our bit b is 1 in both I and j, right? And then we will solve for this, right? So after you have formed a graph out of this, we can apply 2 steps, right? The first step is forced, right? If your edge weight is 0, then nodes connected via that edge, are also 0. Like nodes, like you can say bit b of nodes connected via that edge is also equal to 0, right? So that is your first step. So after doing the first step, you have to do step 2, in which you will remove the redundant ones. Right? So to check that, you can check if that one is contributing to any edge or not. Check if one is contributing to any edge or not. And then you can combine your answer for all the bits. And that will, now you will have your array A at the end, right? So that is the solution. Yeah. So if you guys want to see the code for this, here's the code, right? So I have my array v first that I need to guess, right? So first of all, I am setting all the bits to 1, right? Because I don't know which bits are 0 or not. So first of all, I am assuming all the bits are 1, right? Then I have my adjacent vector. So that is what I will use to form a graph. So I take in my statements x, y, and w, right? So then I will form a graph out of these, right? So I will add y as a node to x, right, with weight w, and similarly I will add x to y as a node with weight w, right? Then I will iterate over all the bits, right? And this is my step 1. So this is my step 1. So set the bits to 0 where edge weight is 0. So I will iterate over all the nodes and I will iterate over all the edges. So if my edge weight is equal to 0, I will set my bit equal to 0, right? So after doing step 1, I will move on to step 2. So now I have to remove the useless ones. So I will iterate over the nodes starting from 0, right? Because we want to find the lexicographically minimal values, right? And then I will check if the value of the node is 1, right? So I only want to remove the useless ones, right? So I don't care about zeros. So I will check if my bit is 1 or not. So if it is 1, I will check the adjacent nodes, right? So if any of these are ones, that means that node is contributing to the edge already, right? What I'm doing is in step 2, right? So let's say I have some node I and I have some connected nodes, right? So if the value of this node is 1, then I will just iterate over the edges. So if the value of this edge is 1, and if the value of the node connected by that edge is also 1, then that means that one is already contributing to the edge, right? So I am okay here. I am okay here. But if there is a 1 here and there is a 0 here, then that means that the following 0 cannot contribute here, right? Then I have to contribute myself, right? So that is what I'm checking here. So if the corresponding node, right? If the corresponding node after the edge is 0, then I cannot be 0, right? Then I have to be a 1 to contribute to the edge, right? So if the corresponding node after the edge is 0, then I cannot be 0. So my can be 0 is equal to false. So I cannot be a 0 anymore. I have to be a 1, right? So in the end, I will check if I can be a 0. If I can be a 0, I will set my bit to 0. Otherwise, it has to be a 1, right? And there's a special case. You also have to ignore self loops. For example, if you have a node I and there's a self loop, right? The value of this is, let's say, 1, right? So now you have to be a 1, right? You cannot be a 0 anymore, right? So if there's a self loop and the value is 1, then you have to be a 1, right? So if there's a self loop, then can be 0 equal to false. So you cannot be a 0 anymore. So that is the special case that you also need to think about. And in the end, you can just print out your array after you have solved for all the bits, and that will be your final answer. Yeah, so that was it for the code and the problem. And if you guys have a doubt, feel free to ask in the comments, and I will be more than happy to answer your doubts. Or feel free to join my Discord server. I can answer doubts there as well. Yeah, so that is it for the video, and I will see you guys in the next one. Also, if you guys don't know, Continue Newton School is offering a full stack development course. The course is over 6 months long, and it is totally based on pay after placement model, and you don't have to pay anything. There is 0 hidden fees, there is 0 upfront fees, and they are granting you a minimum package of rupees 5 lakhs, and the average package is rupees 7 lakhs, and the highest package is over rupees 26 lakhs. So it is a very great opportunity. Also, all their mentors are from top MNCs like Google, Flipkart, Zomato, etc. Also, they will get you placed into the top MNCs as well, like Google, Flipkart, Zomato. So you can learn from the mentors that are working at those companies, and you can land a job at those companies yourselves. Also, you don't need to worry if you guys think कि यार मेरे को भी coding आती नहीं है, मैं भी fresher, मेरे को बिल्कुल नहीं आता है. The course is over 6 months long, and they will teach you from scratch. So you can still sign up for this. And if you guys are looking for a career in the tech field, this is a very great head start that you should sign up for. And if you want to land a job, I highly vouch for this. And if you guys want to sign up, there will be a link down below, and you can go and sign up from there. So yeah, be sure to sign up for this, and I will see you in the next video. Bye bye.